uh, welcome back to the evening colloquium today on the online workshop that is currently being organized by IACS and IIT Gandhinagar jointly. So today's colloquium will be given by Professor Abhay Ashtekar, and this particular special colloquium session will be chaired by Professor Soumitra Sengupta, who is a dean and the senior most professor at IACS. So I will now hand it over to Professor Soumitra Sengupta to introduce Professor Abhay Ashtekar and then chair the session.
Okay, thank you, Shubhanto. So good evening and good morning as applicable in various parts of the world. I welcome you all to this special colloquium lecture in this 2-day conference on testing GR using gravitational waves. The speaker of today's colloquium is Professor Abhay Ashtekar, who doesn't need any introduction to this audience. So I'll be very brief. Professor Ashtekar did his PhD from University of Chicago and was a faculty member in University of Paris and Syracuse University before he became professor and director in Institute of Gravitation and Cosmology in Penn State University. Professor Ashtekar is undoubtedly the world expert in the field of gravitational physics, where he has many path-breaking and pioneering contributions. His wide range of work encompasses loop quantum gravity, a variable named after him, Ashtekar variable, mathematical and observational aspects of black hole physics, black hole entropy, quantum geometry, quantum gravity in curved space-time, gravitational wave, cosmological constant, and whatnot. He has worked in almost every aspects of gravitational physics. He has received numerous extremely prestigious awards and prizes. And to summarize, Professor Ashtekar belongs to those rare brand of physicists who has opened new directions of research in physics, especially in the field of quantum gravity, a proper solution of which still eludes us for a long time. So we are all looking forward to a very illuminating lecture from Professor Ashtekar, and I now invite Professor Ashtekar to begin this talk. Professor Ashtekar.
Okay, thank you very much. It's a pleasure for me to speak at this workshop. It was a difficult task to choose an appropriate topic because first of all, you should not have too much overlap with what other speakers are speaking about. And but on the other hand, it has something to do with gravitational waves. But I was also told that in the colloquium, there will be people who are not in general relativity or gravitational waves, but other branches of physics. And so I had to choose something which was sufficiently of wide interest. So this is the topic that I've chosen. It is Einstein gravitational waves and the many faces of physical reality. So I'll begin. The first part of the talk will be about some interesting historical anecdotes and mathematical structure of some gravitational waves. But in the second part, I will switch gears and talk about use this particular Einstein-Rosen gravitational waves to talk about some really deep conceptual issues about what we mean by physical reality and how it depends on the theoretical paradigms that we actually use. This work is not new. Over the years, it has been a lot of people have contributed to it, and I put kind of the most important contributions that feature in my talk up here. So let's go to the next slide. So the organization is in two parts, as I said. First, I will talk about the Einstein-Rosen gravitational waves. And there's really a fascinating history that many in the community of gravitational waves probably know about, but not everybody knows, and we'll see how it sort of, it has some surprises. And then I'll just briefly summarize the basic mathematical structure, which is quite simple and should be accessible to anybody who knows Maxwell theory in Minkowski space-time, is flat space-time. And as I said, in the second part, I will change gear and introduce a simple thought experiment, and the thought experiment is really just shining a laser light, but in a space-time, which has two space and one time dimension, so 2 + 1 dimensions, and then describe what happens. What is the nature of physical reality? And we'll see that this nature of physical reality changes quite a lot, depending on whether we switch off gravity, that is Newton's constant, switching it off, then we just have quantum optics, or we switch off h bar, then we have general relativity, but no quantum mechanics, and we keep both g and h bar, and then we have quantum gravity. And the interesting thing is that, as was just mentioned, even though we do not have a definite quantum theory of gravity in 4 space-time dimensions, this particular example is really based on an exactly soluble model in 2+1 dimensions, which has infinitely many number of degrees of freedom, and so it is of some interest. Okay, so let me begin with the first part, which is really this Einstein-Rosen waves and the fascinating history about them. I think most people know that a year after Einstein discovered his equations, that is to say in 1916, he also drew analogy with the Maxwell theory. And just in Maxwell theory, we got electromagnetic waves that are produced by time-changing dipole moment. Einstein realized that in general relativity, if there is a time-changing quadruple, mass quadruple, then it also produces gravitational waves. And this is in striking contrast with Newtonian gravity, where of course there are no gravitational waves at all. And so this really was an incredible insight so quickly after the discovery of Einstein's field equations himself. And this was followed up by other people. And some experts knew about the reality of gravitational waves that come when we go from Newtonian gravity to Einstein's theory. But then 20 years later, in 1936, this might come as a surprise to many people, that Einstein changed his mind. Based on his work with young assistant at that time, Nathan Rosen, here is Nathan Rosen, much later, of course, he sent a paper to Physical Review entitled, "Do Gravitational Waves Exist?" And the same day, he wrote to Max Born, quote, "Together with a young collaborator, namely Rosen, I arrived at the interesting result that gravitational waves do not exist, though they had been assumed to be a certainty in the first approximation." By this, he means if you do weak field approximation about Minkowski space, in this approximation, he had already shown that they do exist. But he says that in full nonlinear general relativity, they do not exist. And he goes on to say that this shows that nonlinear gravitational wave field equations, that is to say Einstein's nonlinear equations, tell us more, or rather limit us more than what we had believed up to now. So Einstein's startling conclusion was that gravitational waves prediction of 1916 was physically incorrect. It was an artifact of a weak field approximation, and the full nonlinear general relativity, gravitational waves do not exist. Now, Einstein submitted 3 papers in 1936. All 3 of them have Rosen as a co-author. As you have probably all heard of these papers. One was called the Einstein-Rosen bridge. The other is now known as the EPR paradox, Einstein, Podolsky, and Rosen paradox, about pointing out some fundamental but rather quote-unquote spooky features of quantum mechanics. And those 2 papers were immediately accepted as they were sent. But the referee, the editor of the Physical Review at that time, had an incredibly good sense of nose. And even though the author was Einstein, he sent this paper to a referee. The other 2 were not sent to a referee. And the paper received an 8-page report. And it is only in the 1990s it became clear who the referee was. And the referee was Robertson of the Robertson-Walker universe, or the Friedman-Lemaitre-Robertson-Walker universe, that Robertson, who was actually a professor in Princeton, but was on sabbatical at Caltech at that time. And this report showed that there was an error, not in the technical derivation, but in their conclusion. Surprisingly, the error had to do with change of coordinates. In other words, they were finding a result which led them to believe that gravitational waves do not exist because of some singularity, but that singularity was actually a coordinate singularity. So this report came, which was forwarded to Einstein, and both Einstein and Rosen had very curious reactions to this report. Einstein was very upset, which was uncharacteristic for him. And he, but one has to understand it in the context, because the first two papers had not gone to referees. This paper went to a referee. Einstein, until then, most of his papers had appeared in the Prussian Academy, of which he was a member. And there, if the Academy member said in the paper, it was just published. There was no referee report. So he was very surprised to get this referee report. He was upset. He just withdrew the paper and from physical review. And interestingly, he never submitted another paper to physical review. But then, history is interesting, but I don't want to go into too many details. But the point is that later Einstein realized that, in fact, in some ways, the report was right, and he modified the manuscript. But by then, the manuscript was submitted to the Franklin Journal, or the Journal of the Franklin Institute, and in the final publication then appeared there. But between the physical review letters and the final proofs, sometime between there, Einstein reversed the conclusion and even changed the title. Instead of saying, do gravitational waves exist? The title was On Gravitational Waves. And now the conclusion was that he says that a rigorous solution to cylindrical gravitational waves is given. And then he says that after encountering relationships which cause doubt, that is to say this singularity that I mentioned before, on the existence of gravitational, on the existence of these gravitational waves, of rigorous solutions describing them, we investigate rigorously the case of cylindrical waves. It turns out that rigorous solutions exist, and then he said. Now, this is interesting because, I mean, the history is complicated. I'm simplifying a little bit, but the point is that this is the first solution of exact nonlinear Einstein's equations, which actually represented gravitational waves. So this history is very, very interesting, fascinating, but finally, there is this solution. So it is natural to ask, why is it that an exact solution was possible? And therefore, this was possible because there is certain mathematical simplicity underlying the solution. And in this slide, I want to explain what that mathematical simplicity is. And this mathematical simplicity is because they assumed certain symmetry. As the title of the paper said, right, that, not the title, but in the paper he said that cylindrical gravitational waves exist. So it was really the cylindrical symmetry that is what being used up here. And this is the assumption. So what does cylindrical symmetry means? I think you're familiar with elementary physics or in electromagnetism, that cylindrical symmetry means that if you got x, y, z axis, so this is the z axis, this is y, this is x axis, then the cylindrical coordinates would be in space only, would be given by rho, which is like the radial coordinate, x squared plus y squared is equal to rho squared, and then phi is the angle on the xy plane, and then z is the height up here. So given a point up here, we've got these three coordinates. Z is the height, then there is an angle phi, and then rho is a distance in the xy plane that we look at. And what one is assuming here is that the waves do not exist, do not depend on either z or on phi, neither of these coordinates. So they only depend spatially on rho, and of course they depend on time. So they depend only on these two variables. And it is this cylindrical symmetry assumptions that makes it possible to write down the solutions. But it turns out that technically what one is also assuming is that there is that the solution does not depend on z or phi. More precisely, it admits two. An important thing is hypersurface orthogonal and commuting Killing vector fields, d by dz, d by d phi. And because of this assumption, these waves, gravitational waves, have a single polarization, which in the usual language is analogous to H plus. Now, the point is that the equations of Einstein's nonlinear equations can be simplified if we factor out the z direction. If we factor out the z direction up here, then we're left with a three-dimensional space, which is just given by the coordinate time and rho and phi. These are the things. And then the norm of this d by dz, the z directional scaling vector field. That defines a scalar field in 3 dimensions. It only depends on t and rho. And so this is just a new dimensional full constant that is introduced in order to get phi to have dimensions of a scalar field. So the norm defines a scalar field, and it also defines a 3-dimensional metric. We've got a 4-dimensional metric, and that projects down to a 3-dimensional metric in the t, rho, phi directions. And the 4-dimensional Einstein's equations, the original ones, now reduce to an equation on the scalar field and the equation on the 3-dimensional metric. So from now on, when I say metric and scalar field and so on, they all live in 3 dimensions. If I'm going to refer to the 4-dimensional quantities, like the metric, 4-dimensional metric, I put a superscript 4 here to say that the 4-dimensional metric is a ZZ component of the 4-dimensional metric. In 3 dimensions, we don't have Z. So we got the wave equation satisfied with the wave for the scalar field, and the 3-dimensional Einstein's equation. So Einstein tensor is equal to 8 pi Newton's constant. Now this is a 3-dimensional Newton's constant times the stress energy tensor that is created by the scalar field up here. So the 4D vacuum Einstein's equation satisfy the 4-dimensional metric up here, turn out to become 2 equations in 3 dimensions, one on a scalar field and one of Einstein's equations. But now in 4 dimensions, it was vacuum, there was no source, but in 3 plus 1 dimension, the true degree of freedom, the gravitational wave degree of freedom, descends to the scalar field. And now I got a scalar field, and its stress energy tensor produces for me the 3-dimensional metric via this Einstein's equation. Again, the single polarization of H plus of the gravitational field, as I said already, is captured in the scalar field up here. Now the point is that furthermore, there is a decoupling. You see, so far the equations are still decoupled because the metric depends on the scalar field, and the scalar field propagates on a background with a wave operator here, the D'Alembert operator here, depends on the metric. But it turns out that because of axis symmetry, because nothing depends on this angle phi, we can make a further simplification. Further simplification occurs. It's not an assumption, it's a fact that phi satisfies a wave equation with respect to the physical metric G in 3 dimensions, if and only if it satisfies the wave equation with respect to Minkowski metric in 3 dimensions. So block with a knot up here is just the standard D'Alembertian of Minkowski space. So this just will be the d minus dt squared minus 2-dimensional Laplacian squared. This 2-dimensional Laplacian squared is now in the rho phi plane, is equal to 0. So therefore, what we can do is we can just, this equation doesn't know anything about the metric G. So we can just solve for this equation and then try to use that solution here, because if you solve this equation, you also solve this equation. I can take this solution here and then try to solve for Einstein's equation up here. So there is a decoupling that occurs, namely I can solve this equation without knowing the metric and then solve for the metric. And that is why this tremendous simplification is what led to a closed form solution. So the Einstein's equation, the first step is to solve the Einstein's equation in Minkowski space, in 3-dimensional Minkowski space. But this, most of you have, even the students have done this. Namely, you can easily solve this equation in 3-dimensional Minkowski space, and the solutions can be expanded out in terms of modes. You got e to the IKT, and because of cylindrical symmetry, you got here ordinary Bessel's functions, j naught of k rho, j naught of k rho. Sometimes they are in fact called cylindrical functions because these functions arise precisely in presence of cylindrical symmetry. So this is really the equation that we got. This is really the solution we got for this equation. And now, since this is field in Minkowski space, we can calculate its energy, or the Hamiltonian, and that is given by the familiar formula. This is the energy density up here. This is a volume element in Minkowski space. And I just factored out the integral with respect to 2 pi. So there should be actually a factor of 2 pi here. So which I missed. And this therefore can be expressed in terms of also the Fourier components, I'll call them Fourier components. These are just constants. So you can choose any of the constants, any constants up here, such that the integral converges and you get a solution. And so these are I'll just call them Fourier components because they have to do with e to the IKT. And so the statement is that this is a familiar formula, everybody knows, the wave number times the amplitude squared in the Fourier space. So this is the formula for the energy. Now we still have to solve the three-dimensional Einstein's equation up here. But it turns out that because of axis symmetry, again, this equation can be solved rather easily, exactly. And the solution is that the three-dimensional metric, or the line element of the three-dimensional metric, is given by this formula up here. If in fact I had just Minkowski space, then this term would not be here, and I would just have these terms up here. But because I got the curved metric GAB, so the curved metric GAB just obtained by keeping this part the same, but adding to the first two terms, adding to in front of the first two terms a conformal factor. And what is this conformal factor? Well, it is completely related to the energy of the solution. This gamma up here, this function coming up here, is just the energy of this solution, in a box of radius rho. So this was the total energy. Rho is going from 0 to infinity. Here, rho is going from 0 to rho. So in a box of radius rho. So this function is just the Minkowski energy of the scalar field. And thus, the solution phi that we obtain up here determines the metric completely. There's no other degree of freedom in the metric. Metric is completely determined once you know the solution phi. The degree of freedom in the system is just in the solution phi itself completely. Now, this method, by the way, for the people in the relativity audience, is completely parallel to that was introduced much earlier by Hermann Weyl to solve four-dimensional Einstein equation. But you're solving them in the static, time-independent, axisymmetric situations. Here, the Einstein-Rosen solution is dynamical. It depends on time and represents waves. It is not a static solution up here. So this is really the first part of the talk. And the conclusion of the first part of the talk is that the simplicity of Einstein-Rosen equations is that you can first solve for the scalar field in three-dimensional Minkowski space, get the solution. Given the solution, you can just calculate the energy of the solution in a box and just define this metric. Then this metric, together with this phi, satisfies the Einstein equations in the 2 plus 1 dimension, and therefore Einstein equations, vacuum equations in 4 dimensions as well. So this suggests now a thought experiment that I just want to sort of mention here. So let us consider the underlying mathematical structure from a 3-dimensional perspective. So forget about 4 dimensions. This is a transition. Up to now, we're interested in solving the cylindrical waves in 4 dimensions, but now we're just solving 3 dimensions. In 3 dimensions, there is a duality between the scalar field and the Maxwell field. This may be surprising even to relativity people because we don't normally work in 3 dimensions. But the point is that if you give me a scalar field phi, I can construct a Maxwell field, if you like, a 2-form, antisymmetric tensor, just by using this formula. This is a 3-dimensional epsilon of the compatible with the metric in 3 dimensions. So you just define this. And then it turns out that if this field satisfies block of phi equal to 0, then FAB satisfies just the Maxwell's equations in 3 dimensions. The second one of these equations is trivial just because I got a gradient up here, but the other equation is not. This equation is trivial because if I take another grad, this is antisymmetric, and this will be symmetric, and therefore there's 0. But this equation is not trivial, and this equation reduces to just this equation up here. But furthermore, there's even bigger surprise, to me at least it was, namely that the stress-energy tensor constructed purely from the scalar field is exactly equal to the stress-energy tensor of the Maxwell field. The functional forms of these a priori look quite different, but with this substitution, you just get equal to that. That means that if GAB phi is a solution to the Einstein-Klein-Gordon equations in 3 dimensions, 2 plus 1 dimensions, then GABF is a solution to the Einstein-Maxwell's equations in 3 dimensions. So this leads us to a thought experiment. Now I'm going to go back and forth between the scalar field and the Maxwell field, treat the scalar field as a Maxwell field. And this is a three-dimensional experiment. So three meaning two-dimensional space and one-dimensional time. So 2 plus one-dimensional experiment. And the experiment is very simple. Just shine a laser light, right? Just shine a laser light like that in 2 plus 1 dimension and describe the physics. You know, what is happening? Describe the reality once you shine the laser light. The special relativistic classical field theory, that is to say, if you ignore gravity and ignore quantum mechanics, that would say we have a Maxwell field FAB in 3 dimensions and a Minkowski metric, which is just given by this. And the Maxwell field, of course, is given by the Minkowski epsilon naught AB times this grade phi, this phi that we got. And this phi, it just, as we saw, is just expanded out in terms of Bessel functions and e to the IKT. And the coefficients phi k are arbitrary. If it's a laser beam, then we all know that the laser beam is going to be this green laser beam up here is going to have some frequency. So if I look at the frequency k, then this coefficient phi k will all be chosen so that the beam has the phi k has a very sharp peak at some k equal to k0. That is the laser frequency that you see up here. Basically, is a very sharp peak up here, 0 everywhere here. So this phi k would be very sharply peaked in this particular way. So now what? So the question is now, what happens? So this was a description of the classical physicists who had said G equal to 0, H bar equal to 0. And now the question is, what happens if we switch on H bar and how does the physical reality change? So that is a question that we will now want to ask. So I'm done with the first part in which I introduced the Einstein-Rosen waves. Second part, I changed the gears and I introduced a simple thought experiment, shining laser light in 2 plus 1 dimension and describe what happens. And now we're going to find some surprises in increasing order as we go down here. So this is what now we're going to switch off. We're going to keep G equal to 0 as before, but we're going to switch on H bar. So we'll get quantum optics. We're going to switch off H bar. So we're switching off quantum mechanics and we're general relativity. What does general relativity say? In 2 plus 1 dimensions, and then we keep both G and H bar. So what does gravity say? And as I said before, that this model is exactly soluble in all these 3 cases, and therefore we can draw exact conclusions in this case. So let's then begin. So what does quantum optics would say about this? So let us bring in quantum physics, H bar not equal to 0, but we dial keep G equal to 0 as before. And then we have just a quantum electromagnetic field in 2 plus 1 dimension, as we saw in this diagram up here. Imagine this is 2-dimensional space and 1-dimensional time, and we just have a quantum electromagnetic field like that. And that's what we're looking at. So a quantum electromagnetic field in 2 plus 1 dimensions. Now, since H bar has dimensions of mass times length, throughout here, since we're keeping special relativity, I've just set the speed of light c equal to 1, not to have too many symbols and not to make expressions more complicated. And therefore, H bar just has dimensions of m times L. So we do not have a mass scale. There's no constant of dimension of mass or length, but we do have ml. And it turns out that this integral, dk phi squared, has dimensions of ml. Because if I put one more k into it, then I get the energy. K is just exactly, that's what would give you energy. And therefore, this is really has dimension of energy dimension will be m times L squared. If I put a k here, I'll get that's not exact. I'll just get back energy up here. So energy is just m. So if I put L here, I get 1 upon L, and that cancels, and I just get energy. So the point is that there is a quantity which has dimension of H bar, and we'll see that this is what leads to the effects now in quantum optics. So in the real world, quantum optics would say in the real world, H bar is not equal to 0, and there are no classical electromagnetic fields. what we have is a quantum electromagnetic field, an operator or operator value distribution subject to the Heisenberg uncertainty relations. The electric and magnetic fields cannot be exactly measured or cannot be measured with exact knowledge. There is going to be fundamental uncertainty between them. And the quantum states of the photons have to be brought in, not a classical field up here. So describing the laser beam by a classical field is an approximation, and its correct description is in terms of a coherent state. So if you give me a classical field, then there's a quantum state psi, which is sharply peaked around that field. So it's a quantum state of photons that is sharply peaked around this classical solution at all times. And so in reality, what we have is this coherent state up here. How is a coherent state obtained? Well, it is obtained by starting with a vacuum state and operating on it by exponential of the creation operator. So you create sort of one photon. If in the linear term, if I expand this in the linear term, there will be one A-dagger that will create one photons, quadratic term, two photons, cubic term, three photons, and so on. They're all superposed, and they're all in the same state. And the same state is really given by this profile, this amplitude at phi k that is up here. And then there is a normalization constant. And this normalization constant for the experts is just the norm of the one particle state defined by this classical solution, defined by that. And its explicit expression is 1 upon h bar times dk times phi k squared. So this dk times phi k squared has dimension of Planck length of Planck's constant, and that is why this comes up here. So this is the appropriate dimensionless normalization factor. If in fact this were infinite, then there is no state. The psi will be 0. I will not get any answer at all. But I need h bar to construct this normalization constant up here. We cannot even get a coherent state without the normalization constant. Now, if once you do have the coherent state, the reality according to quantum optics is the following. The expectation value of the field operator in the coherent state is the classical field you gave me. The expectation value of the Hamiltonian in this coherent state is the value of the classical energy associated with the classical field phi that you gave me. So in the expectation value sense, we do reproduce the classical answer. Furthermore, this state is extremely sharply peaked above this classical answer because the uncertainties in the field and its momentum are saturated. In terms of Maxwell field, it is uncertainty in the electric and magnetic fields is saturated. In other words, the product is the minimum possible allowed by the uncertainty relations. And furthermore, it is equally distributed among the electric and magnetic fields up here. So it is as good as the classical field. It's a very sharply peaked around the classical field. And there are quantum fluctuations, but the uncertainties are minimum possible and they're equally separated. There is no frequency scale, and so the coherent state exists for all classical solutions, for all profiles. I had constructed this profile. This was a K, and I had constructed a profile like that. And the statement is that around some K naught. And it doesn't matter where K naught is, you will get a coherent state. So K naught can be arbitrarily large, it can be very, very ultraviolet. I'll still get a coherent state with all these nice properties that I got up here. But what we do need is that this phi squared, this norm, should be finite. And this phi squared, as we'll see in a minute, does have direct physical interpretation. Namely, it is really the expectation value of the number of photons in the coherent state. So what we do need is that the expected number of photons in the coherent state should be finite. And interestingly, if you look at the uncertainties, they all go like inversely to the number of photons up here. So if I look at the relative uncertainties, that is to say the uncertainty square divided by the expectation value. So this is standard deviation squared divided by the expectation value squared. That is always bigger than or equal to 4n. So n has to be large for the relative uncertainty to be small, and similarly for the Hamiltonian. So it's only when the n is large, there are large number of photons, that you get not too much fluctuation and classical physics. But if in fact n is small, then you get departures from the classical physics. So it's not a big surprise for those who know quantum field theory, namely that you need a large number of photons to recover classical electrodynamics. Otherwise, there are quantum effects the fluctuations are important. Thus, from the point of view of quantum optics, this theory up here, the classical physicist view, who said h bar equal to 0, is conceptually quite wrong because it ignores quantum fluctuations. But the new scale that is set by h bar is really gives us this n, and so long as n is bigger than 1, then that is to say the intensity of the laser beam is high, then the classical calculations provide an excellent approximation. So this is the view of the quantum optics of quantum field theory. Now we're going to just switch gears and forget about quantum mechanics, forget about photons, and just concentrate on general relativity. So what does general relativity say? So now we're switching on Newton's constant, talking about relativistic gravity, but keep h bar equal to 0. Now in 2 + 1 dimensions, Newton's constant has dimensions mass to the -1. And therefore the inclusion of g, we acquire a new mass scale, but there's no new length or frequency scale. So the new phenomena are really triggered by this new mass scale that we have. As we saw, the metric is no longer the Minkowski metric, as we saw when we discussed cylindrical waves. The Minkowski metric is given by that, with these light cones like that. And this is the spatial hypersurface, and the causal propagation occurs inside the light cone. But rather, the metric is now given by a certain conformal factor multiplying t rho part, and then the Minkowski part. So this part is being multiplied by this conformal factor up here. And this gamma is the Minkowski energy of the field in the box. Therefore, this is always positive. And because it's always positive, this factor is always bigger than 1, which says that light cones of this metric in GR open up. So the light cones will not look like that, but light cones will be slightly larger up here in the metric up here for this metric. They open up. That is to the points which are not causally related in Minkowski space are causally related with respect to the physical metric up here. So you would say that such points, the light beam would travel across such points. But surprisingly, because this equation is the same as this equation, therefore light cone, the light still propagates within the Minkowski space, smaller light cones up here. Again, for experts in the audience who might be all surprised because they might think, oh, but it's Maxwell field, so it should, or zero rest mass Klein-Gordon field, so should it not propagate along the light cone sharply? Well, in odd space-time dimensions, this is not true. In even space-time dimensions, light will propagate sharply in flat space. Light will propagate sharply along the light cones, but even in flat space, in odd space-time dimensions, so in 2 + 1 dimensions, this does not happen. There is a propagation within the light cone, so there is no contradiction here at all. But more interestingly, away from the sources, so light cones open up is interesting, but away from the sources, experiments can tell that there is an error if we set g equal to 0, which can be large if the laser beam has a lot of energy. If the laser beam that has a lot of energy, then outside the sources, this is just the total energy in the laser beam. And we can see that this factor is, because in the exponent in particular, this factor can be very large. Therefore, this metric is going to be very different from the Minkowski metric up here. And what happens is that because of this, there is actually a deficit angle at infinity. That is to say the ratio of the circumference to the radius of a circle in 2 dimensions up here is not going to be equal to 2 pi, but is going to be strictly less than 2 pi. So if I got a laser beam, as we had just a while ago, if I had laser beam, I can go very far away, like here, and measure geometry, and general relativity would say that I would find that there is a deficit angle if in fact there is sufficient energy in this laser beam itself. So the view of reality is very different from that of a Minkowski space physics. There's going to be a different metric altogether. So a different geometry altogether. And now there's a second surprise. We can ask how much energy is there in the system. From flat space, we know that the energy is just given by H0. But a careful analysis in general relativity says that the total, the so-called ADM energy, is given by 1/4g times 1 minus e to the minus 4g times H0. See that this is bounded because there's a minus sign up here. Even if H naught is equal to 0, then I just get 1 upon 4G. But if H naught is not equal to 0, then I get something which is with a minus sign here. Therefore, I'll get something which is different from 1. But if H naught becomes very, very large, becomes infinite, then this goes away. Sorry, I made a mistake. If H naught is equal to 0, I would get 0 because it will be 1 minus 1. So I'll just get 0. And if H naught is equal to infinite, then this term will go away and I will get a maximum energy of 1 upon 4G. So the energy here is bounded from above, whereas here energy is not bounded from above. It can be as large as you want. If I do a power series expansion up here, I get a Taylor series like that, but the signs are alternating. Each term up here is unbounded above, can be infinite, can be as large as you want. You can just take the laser beam, make it more intense, or you can take the laser beam and change the laser beam and take it at higher and higher frequencies. This then will increase unboundedly, but this sum, surprisingly, is bounded. So general relativity puts an ultraviolet cutoff. There is no ultraviolet divergence. This is just classical general relativity. And yet, there's a qualitative difference in what we mean by energy up here. No matter how large the amplitude is, how intense the laser beam is, or how large the frequency of the laser beam is, the total energy, which includes gravity, electromagnetic plus gravitational energy, is always going to be bounded above, is always going to be finite. There is no ultraviolet divergence. So this is, again, a striking difference from what we thought quantum optics told us, or classical special relativity told us. They both say that this energy is unbounded above, and now this energy is bounded. And this result is non-perturbative, as we just saw. We really need to sum all these things to get a bounded function up here. If you terminate the series at any order, you will find that H is unbounded. It is alternate signs in the perturbative expansion that makes the sum bounded from above. And the value of the upper bound is 1 upon 4G. As G goes to 0, of course, the upper bound goes to infinity. So we get the classical result that Maxwell field can have, a result without general relativity, that the Maxwell field can have as much energy as you want. It is the presence of the new scale, G. You see, 1 upon 4G is appearing all over the place up here. G is appearing, 1 upon 4G is appearing. That is giving rise to this new phenomena. This scale is available to GR plus Maxwell, but is absent in Maxwell theory in Minkowski space or in quantum optics in Minkowski space. So we get quite a different view of reality. So now that leads us to the last part, which has to do with the reality according to quantum gravity. So now we have something very interesting because we have got both G and H bar. As we just saw, G brings with it a mass scale and H bar brings with it ML. And therefore together, G times H bar is Planck length. So in 2 plus 1 dimension, G times H bar is Planck length, as opposed to Planck length squared, which in 4 dimensions will be Planck length squared, but in 3 dimensions, it is just Planck length up here. That is the reason is because G has different dimensions, in different physical dimensions, if you are in 4 space-time dimension or in 3 space-time dimension. So we got these 2 scales, and therefore new phenomena occur. The boundedness of the Hamiltonian will, of course, will actually continues, but we find new non-perturbative effects as well. Now, at first, this is surprising because we do not have a complete quantum gravity theory. But it turns out that the cylindrically symmetric so-called midi superspace, that means we're truncated general relativity using some symmetries, but we are still kept infinite number of degrees of freedom. If we had kept finite number of degrees of freedom, then we have so-called mini superspace. But here, we kept infinite number of degrees of freedom, those in the 4-dimensional gravitational wave, or those in the 2 plus 1 dimensional Maxwell or scalar field. Those degrees of freedom make it a midi superspace. And this, for the cylindrically symmetric midi superspace, this model is in fact exactly soluble quantum gravity model. And as I said, it has infinite number of degrees of freedom that are neatly coated in the axisymmetric scalar field phi, or if you like, in the Maxwell field, which is given by epsilon ABC grad C phi. Recall that in the classical theory, one first solves this in Minkowski space. So this solution does not know anything about the curved metric, and therefore we can still continue to do it. And then for any solution phi, we can calculate its energy in a box, and then we set GAB to be equal to e to the g times the energy in the box minus dt squared plus d rho squared plus rho squared d phi squared. Then phi GAB satisfy the full Einstein-Klein-Gordon equation in 2 + 1 dimensions, and therefore we can also obtain a solution to full Einstein's vacuum equations in 4 dimensions. Thus, GAB is completely determined by phi. Therefore, when you go to quantum theory, we can just take this equation and quantize the scalar field, or if you like, the Maxwell field, which is dual to it. We can just do that. Take the solution, and from the solution, construct the metric operator. So the metric operator is a secondary or derived observable constructed from the true degree of freedom, which lies in phi hat. And that is what makes us this whole subject tractable. Now, there are unforeseen effects in quantum gravity. As in quantum optics in Minkowski space, we have the field operator phi hat, or if you like, f hat AB, and a coherent state psi of phi associated with any classical solution. You give me a classical solution, then I got a coherent state, and I got all this. And in general, I got a field operator phi hat. The new element is that in quantum gravity considerations, lead us to consider rather complicated functions. For example, h hat is going to be now e to the 4g times h naught hat here, and g hat rho rho. So I just looking at one component because I can look at g hat tt if you like. I just happen to just look at g hat rho rho for spatial reason, just for concreteness. Then I can just get this operator up here. So these operators are really derived from the operator phi hat, but they are very complicated operators. In quantum optics, one doesn't normally consider such operators, but now we are led to consider them because they have direct physical meaning made available by quantum gravity. So let us fix the coherent state psi of phi, and for simplicity, explore just the region outside. I mean, I could also look at what happens inside the laser beam, but this colloquium, I don't have time to go into those technical details up here. And so just look at what is happening up here. And remember that out up here, there was a deficit angle. So we just now look at in classical relativity. Now we're looking at what happens in the quantum gravity to the metric up here and the Hamiltonian of the total Hamiltonian of the system. So the metric up here and the total Hamiltonian of the system. Well, I calculate the expectation value of the metric, which is just this object up here, except that now I'm at infinity, so I can just take h naught up here. And similarly, I can calculate. I made a mistake up here. This should have been a minus sign, not plus. Yeah, that was a typo. Okay, and here I got a plus sign. So therefore, you calculate the metric and here I got the minus sign. So here we get here the expectation value of the metric and the expectation value of the metric up here, and you get an expression up here. The expression, as you can see, is rather complicated. I get the amplitude, which comes like phi k squared up here which comes from the laser beam. And then, however, I got here exponential of gh bar times k minus 1. And similarly here, I get gh bar k minus 1 with a minus sign that comes from this minus sign up here. So the interesting thing is the following, that when we did quantum optics, the point was that when I took this expectation value, right-hand side was completely classical. There was no h bar here at all. But now in quantum gravity, if I look at this geometrical observable and the total energy, which are both non-perturbative, then the h bar continues to exist even in the expectation value. So unlike in the quantum optics case. Thus, even in coherent states, the expectation values of key physical observable, the metric and the Hamiltonian, are different from the classical values. This was not the case in quantum optics, but now it is different because these operators are rather complicated operators that are not considered in quantum optics. So then we are led to ask, when is the classical approximation, classical general relativity, going to be good? Well, since we have length scale, gh bar, the Planck length up here, we can consider the limits. We can consider the low frequency limit, where the frequency is low. So this is much less than 1. or the high frequency limit when that is much bigger than 1. Now in the low frequency limit, we can expand out, we can expand out these exponential factors explicitly and see what one gets. So for the metric we get, this is equal to the classical metric, but then there are terms which depend on h bar that remain. Classical metric plus quantum effects remain even in the expectation value. And so if we assume that not only gh bar k is small, but the number of photons times the square of this quantity is much smaller than 1, then we get an expansion, and then these terms can be ignored, and we got a classical solution. But remember, this is now tension, because for fluctuations in phi hat to be small, for fluctuation in the laser beam to be small, we needed n to be much bigger than 1. And now we're asking that n times this should be much smaller than 1. So that means that this quantity, the frequency up here, should be really very, very small and should go inversely as n. If both these conditions are satisfied, then the classical description of a laser beam and curved space-time is correct. But if either of them fails, then that description is not correct. And I'm going to come back to that at the end. What about high frequency? Well, if the laser beam has trans-Planckian or close to Planckian frequency, then all bets are off. Then the quantum expectation value, the quantum metric is, oops, this is incomplete, so just forget it. I forgot to write complete. The next part, so that is just incomplete. So what I obtain up here is really exponential of n times g and h bar cannot, and it is not at all equal to, this should not equal to at all anywhere like classical metric. It's completely different from the classical metric. There are deviations of the order of, huge deviations even from the classical metric up here. So h bar remains a leading term, and that gross departure from the classical theory. It gets worse as n increases, that is to say, as phi classical becomes a good approximation. As n increases, the classical, the quantum, the expectation value of the quantum field becomes close to the classical field, but the metric is fluctuating widely. Even if n is approximately equal to 1, when the fluctuation in the classical field will be large, k naught, and if k naught happens to be close to the Planck frequency, then you get fluctuations of the order of 10 to the 3. Normally we want fluctuations to be of the order of 10 to the minus 10 or something. So here you get 13 orders of magnitude larger than what we want. So the laser beam, where to have a single photon of trans-Planckian or Planckian frequency, there are huge fluctuations in the geometry, even away from the laser beam. And this is the surprise. For fluctuations in the metric and for the Hamiltonian, situation is completely similar. At low frequency, the dimensionless fluctuation is small if and only if n, sorry, this is too many mistakes here. If n is much bigger than 1, if n is much bigger than 1, and if in fact this quantity up here is much smaller than 1. So again, the same equations come. So there's a very severe restriction on the frequency and the number of photons for us to have this classical limit to be relevant, to be good approximation. And a high frequency, the classical limit is just bad. There are huge fluctuations in the metric even away from the laser beam. The situation in the Hamiltonian is exactly the same. At high frequencies, there are gross departures as from classical general relativity as well as quantum optics. So which is just part 2b. The low frequencies, on the other hand, classical GR is recovered if these two approximations hold up here. The same thing, that number of particles photons is very large, but the frequency is very, very, very low compared to the Planck frequency. So one might wonder, why is there this dramatic difference between quantum optics and quantum gravity? It really is because of these nonlinear functions, as we were talking about before. And what happens is that nonlinearities of Einstein's equation magnify small matter fluctuations to huge fluctuations in the Coulombic part of the gravitational sector. As we saw before, the true degree of freedom is in the in general relativity, the true degree of freedom is the scalar field. And the metric is completely determined by the scalar field, right? Once you have the scalar field, the metric is completely determined up here, as we saw. Yeah, the metric is completely determined by the scalar field. This is the energy in the box, therefore the metric is completely determined by the scalar field up here. So it is really what is happening is that it's not the transverse or the radiated degree of freedom that is causing the problem. Small fluctuations in the radiated degrees of freedom are magnified by Einstein's nonlinearities into huge fluctuations in the metric, the Coulombic part, the gravitational sector. And there are specific nonlinearities are important. After I'd done this work, Norbert Straumann, who is really a great physicist, he asked me, but what happens in 2 + 1 QED? So I worked this out, and 2 + 1 in QED, this does not happen. So if I looked at 2 + 1 quantum electrodynamics, so we are replacing the gravitational field by the Maxwell field, and the Maxwell field by the charge scalar field. If I did that, then similar effects occur. But when you do the calculations, the fluctuations in the true degree of freedom, namely the charge scalar field, are not magnified hugely into the Maxwell field. So this really is something very beautiful lesson that we have for gravity, and particularly Einstein's general relativity equations. Okay, so this is basically the part 1, which was the Einstein-Rosen waves. Part 2 was simple thought experiment. We saw what happens if we had quantum optics. We saw what will happen in general relativity. And already in general relativity, there are surprises. Non-perturbative effects started becoming important. Quantum optics, we learned that number of photons has to be large. Otherwise, you don't get the classical limit well. And in quantum gravity, we saw that, in fact, we got the completely new effects. Namely, there's a tension between number of photons being very large and having small fluctuations, even when the laser frequency's tame is very, very small compared to the Planck scale. So this brings me to the last part, which will be the summary and discussion. So summary. What we considered is a simple thought experiment: switch on a laser and describe what happens. We found that 3 strikingly different descriptions of reality emerge depending on which theoretical paradigm one uses. If we use the paradigm of quantum optics in Minkowski space, so h bar is not equal to 0, but g equal to 0, there's no big surprise because we have known this theory for quite some time. That's why there are no surprises. The space-time geometry is, of course, tame, just Minkowski space. And the description of a laser beam by classical field is adequate if the coherent state with a large number of photons, we have that coherent state. Then we saw general relativity. There are surprises. General relativity, the space-time geometry is not Minkowskian, even in the asymptotic region far away from the laser beam because of the deficit angle. But more interestingly, there's a non-perturbative effect, which is that the total energy is bounded up from above, irrespective of how intense the laser beam is and how high the laser frequency is. And that is in particular because there's no, because in general relativity, we have a mass scale, but we do not have a length scale. So we don't know what we mean by high frequency. On the other hand, if we look at g not equal to 0, h bar not equal to 0, so quantum gravity is again ultraviolet finite, but there are surprising limitations of both these descriptions because it is unforeseen tension. We need the number of photons to be very large to be able to ignore quantum fluctuations of the Maxwell, the scalar, in this case, this duality field. But we need this equality to be able to ignore the quantum fluctuations of geometry. In LIGO, for example, we needed some intuition, so I just picked out some number. In LIGO, the laser beam provides us about 10 to the, I think it's about 200 watts and it's about 1064 nanometer wavelength. So it provides us about 10 to the 21 photons per second. So in a second, we got 10 to the 21 photons of beam. So just a pulse of a second, this is what we will have. So this will be 10 to the 21. So that means that even if we are 10 orders of magnitude below the Planck scale, this fluctuation will be of the order of 1. Not not at all negligible. So that is really quite surprising up here. There's a classical description of reality fails in what a priori looks like tame circumstances. Although there is a large sector of classical solution which approximate reality well, it is subtle. We need both these conditions up here. And by the way, one can also see that semi-classical gravity, which is supposed to satisfy the equation. So semi-classical gravity is supposed to be an operator value, operator field, a state of the operator field, and a classical metric satisfying the field operator equation and semi-classical equation where the stress and energy tensor is replaced by the expectation value. This has this completely parallel unforeseen limitations away from the Planck regime. Both fail to incorporate large quantum fluctuations in geometry away from the laser beam. So there are some interesting aspects of reality we learn from different theoretical paradigms. Finally, the nature of physical reality. This detailed comparison was possible because the model is exactly soluble in all the three theories, and the specific nonlinearities of Einstein's theory and non-perturbative effects combine to give this dramatic change of descriptions of the physical reality. The simple thought experiments serve to bring out the fact that what we consider as physical reality is deeply rooted in the theoretical paradigm. You can just say, well, I'm shooting this laser beam, the geometry is this, the laser beam is described by, say, Maxwell field or something. And the thing is that description of physical reality is wrong as soon as you bring in H bar or as soon as you switch on G. And if you switch on both of them, the description you get is very different. If you switch on both of them, then even away from the laser beam, there are fluctuations in the quantum geometry, provided the frequency is not very, very low compared to the Planck frequency. So these are kind of interesting aspects, qualitatively new features that emerge each time we made a paradigm shift. So as the paradigm changes, we discover deeper theories that encompass more and more phenomena. We acquire new constants of nature, and each constant of nature brings new scale. And each scale in turn has the potential to alter the nature of the physical reality at that stage. So that is a surprising thing that we saw. So I began with Einstein-Rosen waves in 4 dimensions, but then went to 3 dimensions for technical simplicity in the rest of the talk to make the implications transparent. But we can really lift these results back to 4 dimensions. Just setting this G equal to 1 for simplicity, not to clutter this transparency too much. The 4-dimensional metric then is actually given by dz squared times the norm of the Killing vector field, d by dz Killing vector field, plus e to the minus 2 phi, so is 1 upon the norm, times the 3-dimensional metric up here. And so it looks like that. And you can see that, again, the true degree of freedom is in phi. So in quantum, I could do quantum gravity here, code the true degree of freedom here. And then we will see that there are going to be fluctuations, quite a lot of fluctuations coming in from here. And those fluctuations still survive. This is linear in phi, but then this term has quadratic in phi. Therefore, this term still continues to dominate over this term. This gravitational wave space-time is not asymptotically flat in 4 dimensions, and therefore is not considered to be of direct physical interest. And I completely agree with that. But being exactly soluble, it provides an excellent arena to do non-perturbative calculations, leading to surprising results. Okay, thank you.
Okay, so we thank Professor Ashtekar for this extremely revealing and thought-provoking talk. It's just a wonderful talk. So now it is open for questions. So I request the member of the audience to ask questions by unmuting themselves, but please don't try to cross-talk and just, try to ask question one by one.
So if you want to ask questions, just write in a chat. I'll make you unmute. Yeah, please go ahead. Shao, please go ahead.
Thank you very much for this very interesting talk. So I'm just wondering about if you change the coordinate system in this problem, where the conclusion change. So now you are using a particular coordinate system. So if you want to perform some significant change in the coordinate system, how does it change? Thank you.
Yeah. So can I answer now? So.
Yeah, sure. Please.
Yeah. Okay. No. I think yeah. You misunderstood the part that I said about Einstein and Rosen. There is a physically correct way of looking at the problem, but you can always choose wrong coordinate systems and come to wrong conclusions. Just take Schwarzschild metric. In the Schwarzschild metric, for a long time, people believed that what we now call the horizon is a singularity, because in the ordinary Schwarzschild coordinates, the metric, some metric component blow up and some metric component go to zero at the horizon. But it doesn't mean that physics depends on the choice of coordinate system. It's just that there are correct coordinate systems and there are coordinate systems whose range fails. The same thing is true with cylindrical waves. Namely, that the coordinate systems I told you are good coordinate systems. Their range is valid everywhere. And so you can make transformations which are, C1 transformations, C3 transformations, so that the curvature tensor is all well behaved. Choose any coordinates which are related to these ones by thrice differentiable functions, and they're also good transformations. There's a complete diffeomorphism invariance. There's no issue about coordinate dependence. The point is that Einstein and Rosen actually made a mistake. Not that they were saying that the results depend on the choice of coordinates. As in the final paper, the final version of the paper, they did use the correct coordinates and there was no singularity. So in general relativity, there are physical singularities and there are coordinate singularities. And one has to keep those two things separate in mind. And what I talked about here has absolutely no problem with diffeomorphism invariance.
So please go ahead. Pancha Pakaram, you can go ahead. Hello, you can go ahead. Ask the question. Panchapakashan, you can go ahead and ask the question.
Can you hear me?
Yeah, now we can hear you. Hello, Panchu. It's great to hear your voice.
Yeah, that's right. I wanted to know if you go to a general relativity with the cosmological constant, will these ideas be applicable because you are not then worried about the asymptotic flatness?
Yeah, so I think there are Einstein-Rosen waves in presence of a cosmological constant. And the statement is that the situation is not going to be very different from, it is different, but for the perspective that you're talking about, it's not going to be very different. Because if there is a space-like Killing vector field, right, then in presence of a cosmological constant, even if you go away towards spatial infinity, so just talk about going to spatial infinity, don't worry about null infinity, then again you will find that the curvature does not die off sufficiently well in 4 dimensions. But if you factor out by the d by dz Killing vector field, by the translational Killing field, and go to 3 dimensions, then again there is then similar to what happened just now, there is no problem, but the description is slightly different.
Thank you. Thank you.
Yeah, so it does not qualitatively change the picture that I was talking about here.
So there's another question by Emini Kutluk. Please go ahead.
Hi, I have a question about this ADM energy.
Yeah.
So this 3-dimensional metric, is it asymptotically flat? How is this ADM energy calculated? Can you make some comments?
So we have to. So first of all, in 3 dimensions, you have to. Any dimension, you have to be careful about what do you mean by asymptotic flatness, right? And this work was done in great detail. At Spatial Infinity, this work was done in detail with Madhavan Varadarajan. So that is a paper in the archives, you can find out the two of us together. Talking about, first of all, developing what you mean by asymptotic flatness, and then, doing the Hamiltonian framework, making sure that the Hamiltonian is differentiable function of the phase space, and getting the metric and showing that this is the form of the metric. And then several years later, I worked with Ishi Bijak and Ben Schmidt, and we constructed the null infinity description of this metric. And it's also asymptotically flat. Again, the asymptotic flatness notion in 4 dimensions cannot be just taken over, but there's an appropriate and well-defined asymptotic flatness notion in 3 dimensions. And we do have the framework about asymptotic symmetries and Bondi energy and such thing. And that Bondi energy is completely compatible with this ADM energy that I'm writing down up here. So the answer to your question is that, yes, it is asymptotically flat, but what we mean by asymptotically flat in various dimensions has to be, adapted to the dimension. And so in 4 dimensions, we want, for example, the metric to go to infinity as flat metric plus 1 upon r corrections. In 5 dimension, it will be 1 upon r squared corrections. So in 3 dimensions, you have to be careful about that. And that work was done.
Sorry, can I ask something more? So when we uplift this theory to the 4-dimensional, does it say about the limits on energy or something?
Right, good. So the statement is that if you lift it up to 4 dimensions, then of course the metric in 4 dimensions is not asymptotically flat. And again, there is a theorem that I proved with Vasilis Alexandropoulos and various people, which shows that if you have a translational killing field like d by dz, then the metric cannot be asymptotically flat, just because as soon as a translational killing field or any killing field, then the curvature is constant. It doesn't change if you make a diffeomorphism along that killing field. And so if d by dz is a killing vector field, then if there is a curvature inside, that curvature will be constant along its integral curves, and it will go out to infinity. So it's not asymptotically flat in the standard 4-dimensional sense. But again, what one does is one gives meaning to this asymptotic flatness through the fact that it is 3-dimensionally asymptotically flat. So if you like, you can talk about it in terms of cylindrical symmetry. So cylindrical symmetry is like d by dz. Nothing happens for infinite range of z coordinate, but you could just make identification in the z coordinate and some distance, and then instead of a line you have a circle, and then you can look at that metric, right? So that it's not really. So now the topology at infinity is different from the topology that you normally have, but you can talk about in that space-time you can talk about what happens to the curvature and so on in the other 2 directions. And then the interpretation of the 4-dimensional energy is really energy per unit length. So the interpretation of the 3-dimensional energy in 4 dimensions is the energy per unit length in z direction that is bounded from above. But so therefore, if in fact you have made the identification, then the total energy would be bounded from above. If you have not made the identification, then you really it's so badly not asymptotically flat that the notion of energy doesn't really make sense.
Okay, thank you very much.
You're welcome.
Hi, Gautam, you can go ahead and talk. Gautam Manna.
Hello. Hello.
Yes.
Thank you, sir. Your fantastic talk. My question is, what is opinion about LQG, and is your model described by LQG theory? And another question is, spin form theory is physically realizable, and and also another question, GW space-time is not asymptotically flat. Also, we have the Bariola-Vilenkin type space-time also the not asymptotically flat. So is there any relation about these space-time?
Right. So maybe I should start in the reverse order. So the statement is that these spacetimes are not asymptotically flat in different senses. And so there's no I mean, there's some qualitative relation, but in detail, the asymptotical flatness fails in different ways for cylindrical waves and for the Vilenkin-Barrow space-time that you're talking about. I just want to clarify for everybody that this is not a physically realistic model of what would happen for gravitational waves, right? In other words, here, the cylindrical waves will be produced by something which is a source, which is pulse, which is changing its quadrupole moment, and which is infinite cylinder. Now, I mean, such sources don't exist in nature, but as we know that in elementary physics, we often use, Maxwell field or magnetic field of a current in a wire, and there we assume cylindrical symmetry. So can you not do the same thing here? Yes. So we could do that, and in that case, you would be able to, if the cylinder is really finite, then cylindrical symmetry is a good approximation close to the cylinder. If you go in the rho direction, sufficiently far from the cylinder, if, for example, the wire has a length L in the z direction, then if you go in the rho direction away from the wire, much more than L, then the cylindrical symmetric approximation is going to be bad. It's not going to be fail. But close to the wire, it looks very cylindrical. So, for example, if you had a source which was, I don't know, center of a galaxy or a big thing, which was, say, just to be dramatic, say a light year cylinder somewhere, then this solution would be quite okay for about a light year in the transverse direction, the rho direction, away from that source. But this solution would not be okay in the asymptotic region. And I mean, we better be, if it is we better be far away from it, if in fact the waves are strong enough. So very close to some sources, this might be a good solution, but it's a very, very limited approximation. Your other two questions had to do with quantum gravity, loop quantum gravity, and spin forms. So these particular ideas about this solution can be taken over to the Hamiltonian framework of loop quantum gravity. And, those of you who know that Hamiltonian framework is based on kind of connection variables that is emphasize a metric, but that defines it. And that what one finds is that actually some very nice results, namely the so-called holonomies or Wilson loops of that connection are actually well-defined operators in the quantum theory and so on. So the Hamiltonian framework, one could take over this, one could describe this model. What is not clear is how to do it in the spin form model yet, because people have not, I just looked at the spin form so seriously in presence of matter, and so I think that there are no detailed results there. But for Hamiltonian framework, this model can be analyzed, and there are some very nice results that were obtained in collaboration with Monica Pierri, P-I-E-R-R-I.
Okay, so Abhay, there is a question from Aviru Ghosh. So he said that you mentioned that the LIGO laser beams, so it is in the chat, so I'm just reading.
Yeah.
You mentioned that the LIGO laser beam, as they're currently operating, would lead to non-negligible effects due to quantum fluctuations. Would you expect this to be affecting the current measurement or inference of source properties because of an incomplete understanding of noise?
No, thank you for asking this question. Maybe I should not have brought. So what the question is about, so let me clarify. This slide up here, where I say this. Okay, so here we're talking about this quantum gravity thing, but really we're talking about three space-time dimensions, right? So where the gravitational waves are cylindrical, and then we needed n bigger than 1, and these conditions together, and then we talked about this LIGO beam and so. Now, only reason I brought in LIGO beam was because I thought the audience may not have a good idea about what one can produce. So LIGO, of course, operates in 3+1 dimensions, not in 2+1 dimensions. So I'm really comparing a little bit apples with oranges, but then I don't know how to give any number in 2 + 1 dimensions. And that's why I just brought in this number up here. So the statement is that in the analysis really was done for cylindrical waves, not for the kind of waves that one is actually looking at. And the statement is that the geometry that was assumed was that produced by the cylindrical waves. The geometry at the LIGO beam that is produced is, of course, Minkowski geometry with some corrections, and those corrections are coming in from the gravitational wave themselves. And these corrections are, we know, in 4 dimensions are very, very small. So in 4 space-time dimensions, the quantum gravity effects on the LIGO beam are completely negligible. I just mentioned this LIGO to get a number, because otherwise I did not know what number to use. I could have just pulled this number out. So I just said, well, in 4 dimensions, LIGO beam has so many photons. So let us close our eyes and just happen to look at our thought experiment, which is in 3 space-time dimensions, and assume the same number. But it really is not a physical implication for the LIGO beam at all, because the geometry there is completely different from the geometry that I would obtain in these 2 + 1 dimensional cylindrical symmetry spacetimes. But thank you for asking this, because some other people might also be confused about it. I hesitated a great deal in bringing this up, but I thought, well, that may be one.
Okay. So we'll take last 2 questions. So Gulam, please go ahead.
Hello. Hi, Abhay. This is Gulam.
Hello, Gulam. Good to talk to you.
Yeah. So actually, my question was exactly related to the last question. I would have asked the exactly reverse one. Suppose we don't see anything, any signature, although I agree with you that 2 + 1 is 3 + 1. But say LIGO, we do not see any quantum gravity signature. Would that put a big question mark on the quantum gravity approach, in the sense that we will never be able to detect anything in near future, or maybe even a considerable amount, because that is a very strong energy that we have, right, in the laser beam.
Very, very good. Thank you. So the question is really about whether we'll see quantum gravity effect in the laboratory. Okay. And in other words, is there going to be geometry in the laboratory such that quantum gravity is going to be important there? And I agree. That, I'm now giving my personal view right here. I'm not saying that this is what is a fact or something, but my personal view is that yes, I think it is very, very unlikely that in foreseeable future, even extrapolating the way that technology is increasing, in foreseeable future, that one would be able to see effects of quantum gravity which are created in the lab. I mean, there may be analog experiments, that's very different, but that the direct effects of quantum gravity. So in my view, the direct effects of quantum gravity, the best place to see them is in the very early universe, and possibly in what general relativity says would be black hole singularity. So in my view, you need really those regions. Now, those regions are not going to be available in the laboratory, but whatever physics took place in those regions could leave a signature in our observations that we perform from Earth. These will be subtle signatures, but one might be able to see them. And just because you asked this question, maybe other people are also interested in it. One such example of the signature was discussed in the Physical Review letter that was published with 2 of my Indian, 3 of us are Indians, namely me, and there is Brajesh Gupta and Srinath, and also with Dong Jiang. The 4 of us have a paper which just appeared, I think, a week ago or 2 weeks ago in Physical Review letters, which point out to that already in C and B, 2 of the anomalies could be simultaneously explained by using loop quantum gravity. The fact that it departs from ordinary inflation in the very early phase. So such possibility, there are such possibilities. Again, for those of you who know, or maybe at the borderline, typically any one anomaly is not statistically significant. In other words, it can be realized in 1 in 1,000 realizations. But if you can explain 2 anomalies at the same time with a natural explanation, that is significant, because that would appear only in 1 in a million realizations. And that cosmologists, most physicists would say, is something that is statistically significant. So the fact that LQG could account for 2 of the anomalies in one go is statistically significant. So to summarize, the statement is that my view is that one could only hope to see in the near future, foreseeable future, quantum gravity effects in this indirect manner. Namely, these effects were large in the regime, like near the what general relativity says are singularities, and then they can have ramifications, they can have effects that we could see on today.
Okay, thanks, Abhay.
Sure.
So we have a last question from Sastik. Go ahead.
Hello, am I audible?
Yeah.
Yes, thank you.
Hi, thanks for a very nice talk. I had a query. So you mentioned that when we put in G, we get a bound on the total energy.
Right.
So my question is this.
In 3 dimensions.
Right, yeah. So in 2+1 dimensions only, when we put in both G and H, so would there be any kind of restrictions on the permissible quantum states of the field, or?
No, so that's very good. So the statement is that we bring in both, and now what I can do is really, I can take this. This is again the slide that you see is really the quantum gravity slide. So quantum gravity and unforeseen effects up here. So here I'm just looking at any phi that I want up here. And then there's a coherent state picked on that, and that is perfectly in the Hilbert space of the quantum system. And that is a Hilbert space of the true degrees of freedom. And then we got these operators operating on that, and we get this number up here. And that is the other way around, namely that the non-perturbative Hamiltonian operator is such that no matter what state you choose, what coherent state which is you choose up here, where it is peaked, the total energy is bounded. The expectation value of the Hamiltonian is bounded up here. This operator is a bounded operator. Actually, one can show it's not only the expectation value, but one can show that this operator is actually a bounded operator. That does not put restrictions here. It is really the fact that the operator is different. The operator has the form that we saw before, which is really the form that the operator version of this equation. Just one second. The operator form of this equation. And the operator form of this equation, that's just a bounded operator there on the full Hilbert space. That's just a fact. And so this is a nice illustration of the kind of ultraviolet cure that gravity can produce. There's a similar analysis with respect to the ADM energy. It's not the same at all, but there's very similar analysis that appears, for example, I think in some writings of Deser, and they also appear in the introductory chapters of my book and so on, that why one might think. Here it is sort of mathematically detailed. There is a Hilbert space, there is an operator, I can calculate its bound. In 3+1 dimension, it's not detailed, but therefore it's an indication that the similar thing would appears to say that there will be an ultraviolet cure for the total energy if you include gravity.
Okay, thank you.
Sure.
Okay, so I hand over now to Professor Soumitra Sengupta for final comments.
I really thank you. But before concluding, I have just one small question that you mentioned about that someone asked you about QED, where this feature didn't show up. I was just wondering that some people are working with nonlinear electrodynamics. So can you comment whether what might happen there?
It's a good question. I don't know. I've not looked at that. I just looked at QED when Norbert Stroman asked me about this.
Right.
I mean, it really depends on whether the nonlinearity. You'll have to look at so I'll tell you what you might want to do. That might be very interesting. What one can do in what I did in quantum electrodynamics was very simple. Namely, what we would like to do is to put the degree of freedom just in the charged field. So the analog is that what was a gravitational field here is like the Maxwell field there.
Yeah.
And
Right.
what was like the photons or the scalar field here is like the charged scalar field there.
Right.
So the system I got is a Maxwell field and the charged scalar field. And what we would like to do is to do some truncation in which the total degree of freedom is all in the charged scalar field.
Yes.
And so the Maxwell field is determined completely by the charged scalar field.
Mm-hmm.
So the simplest way to do it is to consider spherically symmetric sector of this theory. So you might be easily able to do that for nonlinear electrodynamics. So if you consider the spherically symmetric sector, then you are switching off the photons, right? There are no photons if yes. And so therefore there is no true degree of freedom in the Maxwell field. The true degree of freedom is just in the scalar field. So scalar field can be it satisfies this kind of wave-like equation, except that instead of grad, you got grad minus IEAA, where A is a potential. But you can solve this equation in the spherically symmetric sector, and you can express the Maxwell field in terms of the scalar field, because the Maxwell field is just going to be determined by the charge density of the scalar field. It's just Coulomb law that will tell you what the Maxwell field is. And now you can go to quantum theory, in which the scalar field is quantized. You've got Fock space, and then you can calculate what the Maxwell field is, right? Because the charge density is now going to be quantum mechanical. And you have explicit solution of the Maxwell field in terms of the charge scalar field. So you will get the you have a kind of operator for the Maxwell field in terms of the operator, which is charge scalar field. And it turned out that this relation is really rather tame. It doesn't have interesting non-polynomial dependence. The Maxwell field does not have non-polynomial dependence on the scalar field. Now, in the nonlinear quantum electrodynamics that you looked at, that you asked me about, it's a very nice exercise. So one can do the same thing, look at the spherical symmetric sector, look at what happens. And then the question is the relation that determines the Maxwell field, in this case, it's going to be just the electric field, magnetic field will be 0. And then the question is the scalar field, the dependence on the scalar field of the Maxwell field,
right,
is it sufficiently non-polynomial? If it's like exponential, like in this slide that you see that is up here, is it like exponential here, or is it just like this exponential factor, or is it just like polynomial, just squares or something like that? If it is polynomial, then the effects could be magnified, but only slightly. You need something like exponential dependence for the effects to be really magnified. So it will be worth checking that.
Okay, so thank you. And as usual, it was just a wonderful talk. And on behalf of the organizers and all the audience, I really thank you for illuminating us on such an interesting area of physics, where we get such beautiful ideas, new thoughts. Thank you, Abhay, again for being with us.
Okay, so it's my pleasure, and good evening to all of you, and thank you for coming in spite of the fact that it's quite late.
Right. Thank you.